In this video, we'll cover the naming of alkenes. So in terms of the functional groups that we've looked at so far, the alkene is higher in priority than our R groups, so our alkanes, or our X's, which are our halogens. So you'll name the chain so that the alkene has the lowest number possible, despite what else is on it. So let's look at an example. Okay, so we look at this guy and we want to give the alkene the lowest possible number. So if I start numbering from the right hand side, it would be 1, 2, 3, 4, 5. If I start numbering from the left hand side, it would be 1, 2, 3, 4. So since it's the highest priority, I'm going to start numbering from the left hand side. So I'm going to have a double bond at the 4 and 5 position. We give it the number that comes first, so this will be a 4 position. My overall chain is 9, so I'm going to have a nonene, specifically 4 nonene here. I also have a bromo substituent and a methyl substituent. And then when I have a double bond, I want to look at whether the groups that are the highest priority are on the same side or opposite sides. So what you do is you look to see what else is on your double bond on each side, and you assign a priority to each half of the double bond. So on carbon 4, I have a carbon 3 coming off of it and a hydrogen coming off of it. So let's see, I'm going to change colors here so we can see. So I've got this H here. So my carbon is going to be a higher priority than my H. So this would be 1 and this would be 2. And then on carbon 5, I also have an H coming off of it. So there's an H right here. The H has a lower atomic mass, so it's a lower priority. This is like what we did when we assigned R and S. And so carbon 6 is coming off of it, so that's 1 and that's 2. Since my 1 and my 2 are on opposite sides of one another, then this is going to be an E double bond, describing that the higher priority groups are opposite one another. So I'm going to put the stereochemistry of the double bond out in front, and so to name this, I'm going to switch back to red here. I'll start with 4E. So I'll put it in parentheses. 4 tells me where the double bond is. E tells me the stereochemistry of the double bond. Then I will put the functional groups in alphabetical order. So that would be 7 bromo, 6 methyl, 4 nonene. And the ene tells me that I have a double bond. So instead of ane, I have ene there. The other way that I could have done this would be write non 4 ene. So you can put the 4 directly in front of the ene, or you can put it in front of the whole parent chain name, so 4 nonene. So as a molecule, overall, this guy is called 4E, 7 bromo, 6 methyl, 4 nonene. So cyclic systems can also accommodate double bonds. So we'll look at an example here. I want to start numbering to give both my double bonds the lowest possible number. So I can start wherever I want, but I'll definitely start at a double bond. And then after looking at the higher priority groups, we consider our other groups. So the most efficient way to number this so that everything gets the lowest priority possible is to start at the bottom here and say 1, 2, 3, 4, 5, 6. This gives my double bonds the 1 and the 3 position, and then my other substituents end up at the 5 position. If I'd started at the top where I have 4 right now, my other substituents would have gone the 6 position. And of course I want my double bonds to have as low as possible, and 1, 3 is as low as I can get. I have 2 double bonds here, so this is going to be a diene. So that tells me that I have 2. If I had 3, it would be called a triene. If I had 4, it would be called a tetraene, and then we just go on from there. So ene tells me double bonds, the prefix in front of it tells me how many. In this case, I have double bonds. What usually happens in a ring is that double bonds are in a Z conformation, and that has to just do with the cyclic nature of the ring and an inability to accommodate an E double bond because of the steric strain of the ring. So we don't really note the stereochemistry of double bonds in rings unless it is E, because usually it's Z. So if it's not noted, it's assumed to be Z. If it is noted, we would just do that if it was E. So we can say, only note stereochemistry of a double bond in a ring if it is E. Otherwise, it'll be assumed to be Z. So if we want to name this compound, we're going to start with our substituents out front, since we don't need to note the stereochemistry of the double bonds. So put those in alphabetical order. That would be 5-bromo, 5-iodo, 1,3. I have 2 double bonds, so I'll need 2 locants. And then cyclohexadiene. So cyclo, because I have a cyclic compound. When you have more than one double bond, you add an A behind your prefix that tells you how many carbons you have. So instead of hexadiene, it's hexadiene. If there was a 5-membered ring, it would be pentadiene instead of pentadiene. So we have more than one double bond, so we use a prefix, di, tri, tetra, to show how many. We put the A in front of our hex, pent, whatever the number of carbons is. So overall, this molecule is called 5-bromo, 5-iodo, 1,3-cyclohexadiene. So the 1,3 are the locants that tell me where my 2 double bonds are. Lastly, you can have a double bond or a species with double bonds as a substituent. And these systematically named are alkenyl groups, but some of them have common names that are used quite a bit. So if I have just one carbon coming off that is double bonded to the main chain, that's called a methylene group. If I have 2 carbons coming off, so I have an ethene group, essentially, this is called either an ethenyl group, or the common name that is still used quite a bit is a vinyl group. So you'll see something referred to as a vinyl group as well. Another common group is this guy. And systematically, this is my chain where the squiggle is. So if I numbered it, it would be 1, 2, 3. So this would be 2-propenyl, but this guy is often called an allyl group, so as a common name. Another compound that you'll sometimes see is a benzene ring coming off, and if it's just coming off, it's called a phenyl group. So you're looking for your main chain that has the longest chain on it with the most double bonds, and then anything else coming off of it is going to be a substituent. Sometimes those substituents have double bonds. They can all be named systematically, like this 2-propenyl section right here. But some of them have common names, and the most common ones we went over, so that you've got your methylene, your vinyl, and your allyl group. So let's do one example. So we'll look at this guy, and we want to start numbering to give the double bonds the lowest number on the longest chain. So that's going to be 1, 2, 3, 4, 5, 6, 7, and 8. The 2 terminal double bonds can't have E or Z conformations or stereochemistry because they both have H's on the ends there, but that one between 3 and 4 can, and my carbon groups are opposite on that side. So I've got 1 and 1 opposite, so that would be the E conformation. So that will go out first. As a substituent, here I have a phenyl group, and here I have that methylene group. So out front, I'm going to have 3E, so I give it the lower number. And then I'm going to have my substituents in alphabetical order, so L, M, N, O, P. M is going to come first. So I have 6 methylene, 2-phenyl, and then I have 3 double bonds. This is going to be a triene, and I'm going to have a locant for each one. So 1, 3, 7, octa triene. So this is 3E, 6-methylene, 2-phenyl, 1,3,7 octatriene. It's an 8-membered long chain, 3 double bonds at the 1, 3, and 7 positions. It has 1 double bond with stereochemistry, the second double bond at the 3 and 4 position. It is in the E stereochemical conformation. And I have 2 substituents, a methylene at the 6th position and a phenyl at the 2 position.